what's cool about mineral deposits is that it takes a really unique set of conditions to make a mineral deposit. It's not each individual event, but the collection of events all together in one place that causes a mineral deposit to form. They're really rarities in the geology world to have a mineral deposit, and that's what happened here in the Herkimer district, is that we have this unique combination of events that took place. So the new theory is called the oil and seed crystal theory, and as I was mentioning earlier, I'm hoping that this theory will provide better way of understanding all the different things that we see across the district. The Herkimer Diamond District covers about a broad region that's about 60 miles long from north of Middleville down to Fonda. Here's Fonda here. Let's try to try my pointer without turning the thing off. What's Utica? Utica, Amsterdam, Middleville, Little Falls, Fonda. So that's about the district. That doesn't mean there's Herkimer diamonds everywhere. It just means that across this broad region we find a scattered range of deposits. Now, I was just saying earlier, any theory, we hope that any new theory will, as put forth, will try to explain the broad range of features across all the deposits. These little abbreviations might be nice if throughout the presentation, whenever I showed a photograph of something, that I would have these little abbreviations next to the photograph. So if you're saying, gosh, where did that specimen come from, or where does that photograph come from, then you'll see these little initials next to the photographs. So the oil and seed crystal theory looks at the whole district and tries to explain a diverse range of features and why is each deposit a little bit different. It also seeks to try to explain the association of this black hydrocarbon with clear Herkimer diamonds. This association, if you've collected, you'll find this kind of association when you pull, you pull the Herkimer diamonds out. I'm sorry about this. I just bought this, so for the presentation here, so I could do this. You find this. You can see all these clear Herkimer diamonds, all in this black stuff. And this is a new thing that I described. I'm the first one to describe these on my website. And these are these spheres that occur inside hydrocarbon. This is all black hydrocarbon right here. And can you see these cool looking spherical flat planes on the spheres? Isn't that so cool looking, right? I'll show you what these are. I'll show you. I got some more pictures about these, but this is so. These are really small. This is 5 millimeters, just across the sphere, about 5 millimeters. So it's very small, 1/4 of an inch, 5 millimeters, something like that.
Something to add to the presentation, the size. If you add the size, it'll help us.
You'll see that. This is just for the intro. You're going to see size on almost everything. Okay?
And that's only been found at Turtle Clan?
There's another deposit, I think, that some of this, but only these like this, only there, so far as I know.
So what else is inside the sphere?
Dolomite.
Looks like cheese.
Yep. Yep.
Yeah.
That came from the moon.
It does. It looks like it comes from somewhere else, right?
Or it's calcite, maybe.
But I'm going to talk more about the spheres in another set of slides. This is just to talk about this kind of connection between quartz and hydrocarbon, where we find this film on the hydrocarbon, and we find these pockets that are kind of lined with hydrocarbon, and we just see this connection between the hydrocarbon and quartz. So this theory states that mineral forming solutions and oil moved up along fault fractured rock and out into porous layers in the limestone, causing seed crystals to form from which Herkimer diamonds grew. That's the short and simple version of the theory. But you're going to hear the longer version because that's what we're going to continue to talk about. We can find evidence of very similar geologic processes happening over in the Finger Lakes region where they have gas deposits, and they have a very similar kind of setup. We have these fractures, and you have this dolomitized limestone, and you've got mineralization that moved up along the fractures and out along on the beds, and you have gas deposits in connection with both. Oh, so let's go back to the beginning. We're going to have to make these rocks. That's where we start, making the rocks. 600 million years ago, geologists think we had this mass extinction. The whole planet was covered in ice. They call it snowball Earth. And almost everything was killed off except bacteria.
Is that before the plates moved? Tectonic plates, is that before they moved?
That's interesting because when you're talking about plate tectonic movement in the Precambrian, they think that plate tectonic movement was happening from about 1.6. They call it Grenville province. So they think that there was movement happening. So I don't think this is before plate tectonic movement, but because we had a couple of these things, where they call a Gondwana land is like the most recent one, where all the continents they think came together and then they went back out. So they think there were several of these, where they came together, went back out, came together, went back out. So no, I don't think that snowball Earth is before plate tectonic movement. That's a short answer to. But what is interesting is that the plates might have had a slightly different character in terms of the oceans, because of the way the Cambrian oceans are really different. The geologists think that they had really long shelves. If you think about today's oceans, we have trenches. Like if you walk off of New York and you go out 50 miles or so, you start to get really deep ocean water. It drops off and you get really deep. Well, we don't have a lot of evidence for that in the Cambrian seas in connection to where Herkimer and Vermont. I mean, you can almost walk. It's shallow seas, for really long, flat, shallow seas, and you have these really widespread carbonate formations that are really extensive, go for all over. I mean, we have the same rocks that are Herkimer are hosted in are found over in Vermont. The same age rocks, and so we have this really broad, flat oceans. And this is important because we kill all the life off, and then we make these big oceans, and then we introduce the flourishing of a new life form. It's not new, but we get this huge, widespread expanse of stromatolites, and because they don't have anything to compete with them, right? We had snowball Earth, killed everything off. These guys come back and go, hey, there's nobody around anymore. So these guys just went crazy, and they grew all over the place and led to the formation of these big, broad carbonate formations that have stromatolites in them. Now, stromatolites ended up changing texture. They change texture based on the environment that they're formed in. And at the top of the Cambrian, where Herkimers are found, not the bottom, but as you start to get back, go up the top of the formation. At the top of the formation, we think that the stromatolites may have been a little bit different, because we may have had some salty seas, and we may have had, the stromatolites may have had a little bit different texture or shape to them. And this is some research by a guy that's been studying stromatolites forever. I wrote to him and asked him, what about, what happens to stromatolites if we have a salt sea? And he said, well, they just change.
exactly what is a stromatolite?
This is carbonate. It's just all this is calcite or limestone.
Oh, so it's not it's not botanical, or
There are, see those, they can have little thin organic mats, but a lot of the times because of the environment that stromatolites are formed in, there's a lot of competition for organic material. So they're formed on the shoreline like this, so you're not like out in deep water where you get shales with lots of black material in the shales. These guys are on the shallow water, so you have a lot of other, you get little crabs and worms and all kinds of other things running around in this water, and they're all trying to get at that organic material that's being left by dead stromatolite organisms.
Cyanobacteria.
Yeah,
They grow up in chains during the day, and then at night they fall down and they'll trap the little things inside, and that's what give you the mounds over several years.
Yep, this is their actual shells, the shells of the organisms in a sense. But in terms of getting the black organic material, there's not a lot of algae mat material. I mean, not enough where you can say, geez, this accounts for all that black material we find in the Herkimer deposits. It's not even close. And they behave differently. The algae mats behave. You don't make round bubbles inside algae mats. You just don't. You can't do it. So at the top of the Cambrian, so at the bottom of the Cambrian we're like 580 million years. Top of the Cambrian we're about 500 million years, and things start to change. Remember, we had these shallow seas over here, these shallow seas we talked about before. What's happening is we have these radical changes in sea level where the rocks that were buried down here, the limestones that we made and then buried, were being uplifted. And they get uplifted right out of the water and exposed into air. And there's a lot of evidence, geologic evidence, to support that this happened. And it happened specifically with the rocks that host Herkimer diamonds. And this is really important that this happened. And another thing that's interesting is that in the rocks that host the Herkimer diamonds or nearby, we find these really cool breccias, these broken fragments of material inside limestone. This is actually a little broken piece of stromatolite. See the little banding on it right here? So this is these are broken fragments of material that are then re-cemented. And these are found really close to the major fault systems. And what that tells us is that we think that a lot of this uplift is actually connected to faulting as opposed to sea levels dropping. We think it's connected to the earth rising up because we're making this stuff. We're cracking the rock, we're dropping fragments into the mud, and we're cementing the rock again. How do you do that? Well, you lift the rock up through faulting, through seismic activity, and you break it apart, and this is what happens. And we find these things really in connection to these major fault systems. I'm saying all that because this is just the geologic story. So when we lift this up, fault these up, lift these up out of the water, and this is in connection also to Africa and the tectonic orogeny in Africa starting to approach, we can form a karst environment. And a karst environment is basically a cave-making kind of arrangement. And so this is our limestone. See it? Blocky kind of limestone like that. So our limestone, and we get the water comes down, and it ends up going along the bedding layers and down through cracks and weathering out and making lots of holes in the rock. And the top of the Cambrian formation is just chock full of all this weathering, intense weathering that happened. Okay, now we've done it. Now we have our basic system. We've got these major fault systems. We have a stromatolite layer that was ready to be weathered and take fluids. We then rose this up into the earth, we put waters through it, we weathered it out, and then we buried it all. Now, with it buried, we now start to introduce the mineralization into the system. And the first thing we find this broad dolomitization of the limestone. And that dolomitization looks like this. You have these tiny little dolomite crystals, almost like salt cubes, like a little sprinkling of salt. And this is really pretty. You can go into any Herkimer deposit and you'll find these. They're very, very common. That was its normal growth pattern. This is an unusual growth pattern for the same little cubes. They sort of stacking up on top of each other. These are the different mineral episodes. I'm going to go through these and get to the Herkimer diamond. And I'm going to show you pictures of all of these. This is necessary for me to answer some questions about what's going on with the whole region. But I'll show you each of these phases as we go. We just saw the early dolomite, which is the first mineralizing episode in the Herkimer district.
Question on dolomite. You're getting what, magnesium fluids coming up and changing the lime? Is that right?
Yeah. I was hoping no one would ask. No, I'm sorry. No.
I'm not the only one confused as to what is dolomitization.
Yeah, it's a very how it's happening. It is an argument for geologists and scientists of where do we get this magnesium? How is this happening? How does this happen in the whole geologic picture? There's a lot of argument about how does dolomitization on this broad a scale happen? Yeah. Where are we getting all that magnesium to change all this calcite into calcium magnesium carbonate, which is dolomite? So where are we getting all that magnesium? There are lots of theories about where it's coming from, but I don't think there's any really good evidence. I mean, some people are talking about circulating magnesium brines. That brine being, if we take that, remember we've talked about the land uprising, and the seas would then be in small pools. Some of them might be blocked off and be evaporating, turn into these salt brines. And some people think those salt brines may have high magnesium content in it, and then you start to circulate some of those salt brines into the rock. That's one theory. Another theory is that when you start to uplift the rock, you start to compress the muds and the material down underneath, and the very first thing that starts to get released are these magnesium chloride from the squishing of muds that contain salt water in them, seawater, salt water. And so you start squishing that mud and turning it into rock, and when you start doing that, you're releasing this magnesium chloride up into the rock. So those are the two basic theories. The third one is that it's connected to ancient crustal rock. That's how you, like talc. Talc deposits are magnesium-based altered rock. But they think that's a different process than making dolomite.
Okay, that's at least they're coming with some idea. I've never heard good theories before as to where it came from.
Yeah, those are the theories, but there's there's not enough evidence to really substantiate one idea over another.
I can at least understand the squeezing it out of salt water though, because the magnesium would not crystallize, would come out as a magnesium chloride.
Right.
Okay.
Yep.
That's better. I'm getting some idea on it.
Yeah. So let's look at the second phase dolomite. Let's go, okay? Thank you. The second phase dolomite it's very different than the first phase dolomite. It's often blockier and not all of those tiny little cubes. and it can be very etched. This is from Fonda, from Diamond Acres. Can't see it down there, little DA. Very etched crystals. And you can see, again, I keep the size reference up there, and so you can see it. Now, this is how we geologists end up saying which came first. Is that you can see one thing growing on top of another. And now here we can see these really nice, larger, blockier dolomites growing on top of these. Are all those tiny little cubes that cubic-looking things that you saw before. This little scattering of salt-like crystals. And these are the larger crystals growing on top. The same, you can see them over there too. Those are the smaller ones. These are the larger ones. And here's another thing that happens with these larger crystals is you can end up with these beautiful saddles that form with this dolomite. And that's kind of the typical look that you end up with the dolomite when you can have it fresh and not weathered. Another picture of really nice, these nice beautiful saddles and really pretty Druze quartz. It's pretty saddles. And sometimes the second dolomite is black. It's hard to find black dolomite, but it does occur. And I think was a lot more black dolomite. I don't know how much more, but I think there was more. Because what's happening is we end up seeing the black dolomite inside. See it there? You see it over here? See it, the inside of this crystal? This is broken. So you see the inside here, it's black, both of these. Outside is not. And I think there was some kind of process that either altered the black or laid another layer over the black. I don't know. I haven't done any analysis of it. I just think there's probably more black dolomite in the region.
What is black dolomite?
It's a good question. Since we don't have any analysis,
It's just something in the white dolomite.
yeah, iron or hydrocarbon or what?
Some contaminant. No,
Something.
That's what you're saying.
Right.
Yes.
There's
okay.
something there. There's something in the dolomite
Okay.
that's caused it to be black. What it is, I don't know, because we don't have any analysis of it. We do know that its character. If anybody's mined scepters, if anybody's in this association of black dolomite and scepters is pretty common, having that happen. And we know that these black scepters are really black, if you've ever seen one. The rods of these scepters, scepter meaning that you can see it better over there. A scepter is a rod with a Herkimer perched on top. And these are quartz crystals, but these scepters are black as night. If you've ever seen them, they're just really black. So is there some reason that we have black, really black here, and this is black? I'm just pointing out a connection. Third phase. Third phase dolomite is kind of sketchy, but it's just different looking. We ended up with this kind of brick red dolomite. And it really doesn't occur everywhere. There was research done on this, where they actually did some chemical sampling from the interior of the dolomite to the edge of the dolomite. It was done by people at the museum, New York State Museum. And it did show that there was an increase in iron content in the dolomite, heading towards anchorite, anchorite being basically a ferrous dolomite. And this kind of makes sense because the next phase next mineral episode that comes in is sulfides. So if you think of the dolomite being there and then being followed by sulfides, it kind of makes sense. Well, geez, maybe there was a little more iron in the dolomite making solution at this particular time. Sulfides. Sulfides are present, and I think they were really present throughout the district, but so much weathering that we don't get to see them except in districts where we're able to preserve them. These are rods of marcasite and pyrite. And if you look up really close on these rods, I think this is only like an inch across this whole picture. You can see these tiny, tiny little crystals. And I'm going to show you another close-up of that so you can see what they look like. You can get Herkimers growing right around the rods. And the calcite, they were growing on top of one of the rods.
Do they form differently depending on where they are? Like one's inside, one's...
I think this is just the Herkimer, in these two instances, the rods were present and then the Herkimer solution came in, and this one just, grew around it, and that one didn't grow all the way around it. This is an actual sulfide pocket. That arrow down there is pointing to the rods. Can you see the sort of pile of rods down there? I know for the people in the back, probably going to be hard to see them. But they're all kind of laying down here. See them? The rods of like that. And then these are plates. These are big plates of marcasite and pyrite. And that pocket's about 3 feet across. And here's a close-up. And I wanted to note in this close-up, this. Can you see that? See that? That's a second phase dolomite going right around an angular fragment inside the pocket.
What location is this one?
HB2, Hansen Benchmark Quarry, HB2. Yeah, you'd see it, but it's down, it's down there.
Excuse me.
Yeah.
Are you saying that the sulfides came in somewhere around the time when hydrothermal?
Yes.
Hydrothermal water with silica came in?
No, way before. The sulfides are way before. If you can find Herkimers with sulfides in them, and so the sulfides come before the Herkimers, and I think the sulfides come before the Druze, even the Druze event, because I have a few samples of Druze over the top of sulfides, but they don't like to nucleate on each other. I mean, quartz doesn't like to grow on pyrite, and pyrite doesn't like to grow on quartz, so it's hard to see the relationships between the two. But there is overlap, like I just talked about an overlap between the dolomite and the sulfide event, making an iron-rich dolomite. So I think there's no really straight cutoff, except that we know the Herkimers are they come a lot later than this.
Is it iron sulfide?
This is it, iron and sulfur, yes. It's basically iron and sulfur. Iron and sulfur and water, yeah.
Does it have to do with hydrothermal?
Yep.
And maybe black snakerish?
Oh, like where is this? Yeah, I think this is again, the muds are being pressured, and as you squeeze the mud, you're squeezing out things in a certain order. Okay, the more you apply pressure, the more the changes in what's being released from the mud. This is, I said I'd show a close-up. Oh, those are the plates, the plate form for the pyrite and marcasite. And here are the crystals. Like this is 1 millimeter. That's a millimeter. Okay?
That's a big millimeter.
Yeah, that's a big millimeter, right? These are very tiny crystals. Can you see this shape here? It's called a coxcomb. But that's a really classic, like marcasite shape right there. That kind of pyramidal shape, and then you can see these cubes of the pyrite. So this is that marcasite and pyrite mixture that we see. Really, all the plates and the rods are all made out of this stuff, this piled up mixture of these two crystal forms. And this is, you can find this stuff. This is really hard if you're a scientist to try to come across this, because nobody saves this. Nobody takes this home. Okay? I took it home, but I mean, nobody else takes it home. This is one of those plates, those marcasite pyrite plates that I just showed you with all the crystals, that they're not there anymore. It's all been weathered and turned to rust, the same way you make rust on your car. This is just a big little mess of rust. And the guy found a big pocket just full of these, just like the pocket I just showed you of the marcasite that wasn't. But all that was left when they used this, and it all ended up on the dump. Oh, I threw it all out, he said. Well, where? You can also see rust, examples of this rusting of the pyrite and marcasite, where you can see these beautiful rust stain over the quartz crystals. And sometimes, you can see the yellow rust stain. Sometimes you can get this really bright red rust staining in the pockets. Now, and if you're lucky, you'll find these, what are called pyridahedrons. You can see the arrows pointing towards a pentagon face. That's a face with 5 sides to it. 1, 2, 3, 4, 5. You can see it here. Right there's a beautiful face right there. 1, 2, 3. Sorry, my hand's shaking. 5. But look around, you can see more. You can see more of these 5 faces. Okay? Those are pyridahedrons. They're sort of like they ended up, if you put all the 5 faces together, you sort of end up like almost a sphere-looking thing. And pyridahedrons are pretty common as a form for pyrite, but I had not seen them coming from the Herkimer district before. You can find sphalerite. This is this ruby-colored sphalerite. I saw a beautiful specimen from the Herkimer diamond mine with actual crystals. And chalcopyrite. Now you thought that size was, this is 200 microns. Okay, it's probably 1 millimeter from there to there. Okay, that's probably 1 millimeter across the whole slide. And these chalcopyrite crystals are really tiny. See that diamond kind of, a triangle kind of face? That's classic for, and this bright copper, bright golden kind of yellow color. The specimen, when you find it sparkles this bright yellow, bright golden yellow. Okay, so now we're done with the sulfide phase, and we're going to do this early hydrocarbon. We talk about an early hydrocarbon phase because we'll end up with this druze that's black. And that black druze is because there's hydrocarbon dust inside all of these crystals to make it black. And in order for the hydrocarbons to get in there, they've got to be around in order for the quartz solutions to come in and then be able to have hydrocarbons included in the quartz. So we think there's an early episode of hydrocarbons that happened before this. Now this very first druze is characteristic of this form, like pyramids, so it's called pyramidal druze. So you end up with these pyramids, just classic, you find this in geodes, the Brazilian amethyst has this kind of form, but this is the very first druze in the Herkimer district, and it's characterized by this kind of rind, which is also you can find with geodes and agates, and a very low temperature silica form that's in contact with the rock.
have a question.
Yep.
So would that be, so is this early then?
This is the very first quartz event in the Herkimer district.
This one?
This,
Is that early? I'm trying to match it up with your,
oh, that's okay. I think looking at this, it looks like this very first druze. I'd have to take my hand lens to tell you for sure, but it looks like the first druze to me. You can look at it and see if you can see a rind on the wall rock. See if you can see
the white.
white. See if you can see a thin little lines where this druze is in contact with the wall rock. But I think, and see if it looks like all little pyramids to you. Use your eyes instead of mine. But it looks to me like it is. But sometimes you can end up, you're going to see other druzes, and sometimes you can end up having them on top of each other, which is really cool because you can end up having this druze with another druze on top of it, and then a Herkimer's on top of that. And I'm going to show you some pictures of that as we move on. Second druze. Now, remember, the first druze is all these like little mountains in a row. The second druze is more elongated. And it can occur in this kind of fence formation, or stack it up like that. And here it is on top of the first druze. These, you're looking down on the top of the pyramids. These are all these little pyramids of the first druze. And here they are sort of squashed, but they're there. These are the first pyramids. This is the second druze, elongated, stacking up, and these are Herkimers. Now this is a weird occurrence. I haven't seen this anywhere else in the Herkimer district. I've never seen it ever talked about anywhere. And here is that elongated druze, which is the second druze, except instead of being fat or stacked up like crystals or pot, nicely neat, this is like somebody threw them all like sticks. Here, just throw you out there. There you are. And they're all stacked up. There's down here is the pyramid. See the pyramid face? That's the pyramid quartz down underneath it. And there is another druze. And they call this the baby floater druze. And this, I'm going to talk more about this later because it's important in terms of the seed crystal theory. But you end up with this coating of very tiny little Herkimers. The druze zone really varies over the district. This is a pretty big druze zone without any really defined horizontal linearity to it. You could just see the pockets. Can you see them all scattered around? They come all the way down here, and here, and here, and here, and here, and over there, just kind of peppered, scattered throughout the rock. And not just little holes, but kind of these irregular vugs. And sorting out, as I said, sorting out the different phases can be difficult because here we end up having one set of crystals growing on top of another set. This is the baby floater druze. And that's what this is a sample from that previous zone, showing you kind of how big that druze pocket bug is for Herkimer. Sometimes we end up with these horizontal orientation for the druze, which is really, you end up with the druze just combined to this kind of horizontal zone and forming these plates. Instead of that round bug you just saw, this is a thin plate of druze. And I saw a druze plate that was that big in the field. This is just, all this is tiny little quartz crystals, just a plate of them. This, I saw one like that size. And that's I'm holding, that's all little bugs of druids in a horizontal zone. So, second druids, that was the second druid. Let's talk about this late prismatic phase of the quartz. And this is not a druze phase. These are these elongated prismatic crystals, where you just get these long crystals of quartz. And those are the crystals. These long crystals came before Herkimers, because we see the Herkimers growing right over the top of them in terms of forming these beautiful scepters.
You're doing a lot of description of the various stages of deposition of these types of quartz crystals. Do you have any speculation or theory as to why particular crystal sizes and morphologies occur at different times?
I have tried to find some science that looks at PT, or pressure, temperature, chemical variations in connection to variations in quartz crystal habit. And I can't find anything anywhere.
Wow.
I can't find anything published. I'm talking about, I can't find anything scientific anywhere.
It's pretty basic stuff, though, isn't it?
Yeah, under controlled conditions, you know, when you're growing like silica for industrial purposes, I can find some stuff. But when you're talking about trying to apply pressure temperature variation to the natural world and all the different morphologies we see of quartz, nobody has come up with any kind of explanation to say. And in Herkimer, we have, well, you haven't even seen them all yet. Wait till I show them all. I mean, there's so much variation. That was one of the very first things I started to look for. Like, what's going on, you know? Can I come up with something that tells me what the heck is happening here? You know? I think there is something happening. I think that if we talk about this system where we have fluids coming up a fault moving out like this, that we have hotter fluids with more corrosive chemistry in the fault system, or closer to the fault system. That jackstraw druze that you saw, I think that's really close to the fault. All of the material, all the rock around it is all corroded, etched, leached out. It looks like it's just a heavy amount of corrosive activity happening around that. And you don't see that hardly anywhere in the Herkimer district. That jackstraw quartz, really rare. But so if you're right next to the fault, you have hotter fluids, they're more corrosive, they're eating away at the rock, they have different kinds of quartz that are crystallizing out, and then when you move out away, you start to change the morphology. But that is me winging my hat around going, here's what I think is happening, okay?
Excuse me.
Sure.
I was just wondering, at a certain point, that kind of information would be very proprietary.
Which information?
Well, heat, pressure, growing crystals.
Yeah, I think if you came up with some new information, I'm sure. I found some articles, for instance, on people growing quartz in the presence of hydrocarbons, which is very important for this talk. But in terms of overall PT conditions applied to nature, we just don't know. That's what we're, so too much variety, I think, at this point. If I find something, I'll add it because I think it's really important. I'm going to keep looking. I mean, there's a beautiful page, a beautiful site on the web called the Quartz page, and it's, the guy has so much information about quartz on that page. Quartz of all kinds of quartz. Oh, this is cool. We have so we just did the prismatic quartz, those long quartz crystals. Let's get into this. Inside Herkimers, we can find these long crystals, and they occur in calcite too. But we can find these long crystals, and I certainly, when I saw them, I went, what the heck is that? And so I took them to the State Museum and had the guy look at them for me, and under a really high-powered microscope. He said, those are all covered with oil. And I go, yeah, you know, I can believe that. Look at that. It looks kind of like a little glob there around that, kind of bumpy here, and right? He said it looked oil all over those things. I said, well, that's cool. And oil over the top of these long crystals. And if you were to, I said they occur in calcite. So there they are inside the calcite, again gray. If you were to cut a hole in this calcite crystal, have nature cut the hole, not me. Nature cut a hole in the calcite crystal and then over time wash all the oil away. This is what they look like. These beautiful, brassy, long needles of marcasite. It's iron sulfide.
Is that oil fluorescent?
Can't tell you. I mean, I've heard some of people that found fluorescent oil, but I can't tell you if.
The crystals from Pakistan,
Yeah, that's what I was
it's
asking.
fluorescent oil globulars.
Yeah, I've heard that people have seen it in the field. I haven't.
Some of the ones from Fonda do show a bright fluorescence. It looks like oil is fluorescing
Great.
inside the quartz.
That's great. That's good to hear that because I hadn't seen it myself, and I'd only heard that today coming here, but I'd heard people had seen it. So where are we? We're after the marcasite. We're now going to do the hydrocarbon event, and it comes up the same system that we've been using. It's the same plumbing system. And the hydrocarbon occurs lots of different ways. We can end up having this coating over the dolomite. And you look up at it really close, and you see all these round bubble-looking kind of features all over the dolomite. It can be inside the quartz, and this is kind of cool because it's inside. It's turned half of the quartz black and the other half not. So it's like the fluid is captured, the hydrocarbon in the quartz. Hydrocarbon inside Herkimers, turning them black. In veins, or in long elongated vugs, filling them up. It can have this really curved kind of fracture to it. See that curved surface down there? You see it, a couple of curved surfaces down there. They're there. And this one here, this is a big chunk of hydrocarbon, and hydrocarbon is dust. You get this kind of fluid kind of look to it where it fills in, goes out and fills in openings and goes along surfaces, goes up, moves around. Just seems to be moving around, migrating and filling in surfaces. It goes horizontal, goes vertical.
What's the chronology? Hydrocarbon first, then quartz?
Yes.
Herkimer?
Yep.
Because when I've opened up pockets and you see the incomplete Herkimer crystal, it has this curved surface.
Yeah, I'm going to show you that.
And that's the contact
Yeah,
one with the
exactly. It's forming up against the hydrocarbon. You're going to see, I'm going to show you some of them. Yeah. You also get these wonderful inclusions. I bet you these would fluoresce. I'm going to have to try it now that people have mentioned. But these are amber colored and not dark, not black. These are films. So as this crystal is growing, it's sort of captured some of the hydrocarbon and included it within the crystal. You can see it over in that one too. And this is really, really, I said you'd see things you'd never seen before. That's a sphere. That's a sphere. Whoop, back. That is a sphere of hydrocarbon.
How big?
This is about 5 millimeters across. Let me think. I remember seeing it, trying to think how big that is. This probably don't have a size because I don't have it in my collection. I think it's about half a centimeter, maybe it's 7/10. So if you said 1 centimeter, 7/10 of a centimeter, that's what we'd be talking about. It's still pretty small, you know. it's under ½ an inch. And this, you can press on this and it'll bounce back. Okay?
And how old is it?
This the hydrocarbon, I'll talk about how old I think, the hydrocarbon, because we're talking about something that happened after the rocks were formed, okay? And we need to have some kind of idea of when that is. Right now, the leading theory is that it comes with the tectonic orogeny, the mountain building episode, the first Appalachian mountain building episode. There's two mountain building episodes that make the Appalachians, the Catskills. There's two mountain. The first, they think that all of this stuff in connection to Herkimer's, the leading geologists out there think that it's in connection. All these fluids are in connection with the first episode. About 480 to 450. Okay.
But to me, what amazes me is that it can have remained rubbery for that long.
Yeah.
That's just like.
Crazy, right?
Yes.
Yeah, and the fact that this was actually discovered is even more crazy, right? Because this is, some of the things that I'm showing you, there's only one sample in existence because they're so rare. Some of the things are rare for multiple reasons. Stuff just doesn't get saved. When you're looking for sparklies, so much stuff just, okay? No? Some stuff just goes, boom, out to the dump. People don't pay attention to all of these little details that I'm showing you. And it's all these details that help make up this new story that I'm telling you. Somebody was mentioning about spherical surfaces, and that's why I show that, and I show these dimples right on the face of a Herkimer diamond. And that's that. That's those things right there. And this is cool. I showed this before. There's an actual remnant of the bubble. This is a remnant of the bubble in the hydrocarbon. Okay, and again, that's only about 5 millimeters across. Same with this, about 5 millimeters across there. I said I'd talk a little bit more about these guys, and I said I'd talk about these really cool looking flat surfaces. These are actually the beginning of the formation of the quartz faces, corresponding to these. 1, 2, 3, 1, 2, 3, 1, 2, 3, 1, 2, 3, 1, 2, 3. 1, 2. You can't really. This one's hard to see, but you can see this one for sure. And you can, if you look closely, you can see this one. But you can really see 1, 2, 3, 1, 2, 3, right? Yep. That's. This is trying to become this.
Where was that from? Which mine?
This is see TCR. This is all TCR. Turtle Clan Ridge.
Okay. I've never been.
It's private. You won't be there.
Oh wait a second. It's as if you've got that sort of ovoid structure and then it's starting to face out.
Yeah.
It doesn't usual quartz crystal formation go out this way from basically layers on the original form.
Yeah, I think that we have a supersaturated solution, and I think that we have seed crystals in a supersaturated solution. So I think the very beginning part of the growth is really, really fast. We're talking, again, remember this is only 5 millimeters, okay? So I think when we're talking in the range of below a millimeter, I think you're going to find hundreds, thousands of tiny Herkimer diamonds that are a millimeter or smaller. And I think people have collected, how many people have collected pockets and found tons and tons of tiny little Herkimers? Yeah. Yeah, it's that relationship is again, that's another common phenomena in the Herkimer district. Yes.
I'm a little confused, please help me out. So the flattened sides are
Yes.
where the quartz is growing against spherical
No, the faces
hydrocarbons.
the faces are starting to form, and as it's growing, the faces are already forming, but as it grows, it runs into the edge of the spherical cavity.
That's what I was asking.
Okay,
So
and
that's
so it stops because it
there,
runs
but
into
it
the edge.
continues to grow
Right.
between.
So it's starting to grow, but it bumps into the spherical cavity. The faces are not growing after it bumps in.
That's right.
The faces are growing before it bumps in.
So it starts out an oval or a sphere?
No, it starts out as a fluid.
No.
I don't think it's starting as a. I don't know how it's really starting. All I know, I can see the faces and I can see it bumping into the edge. So I think the faces are forming first, and then it's expanding and it bumps into the edges of the sphere before it can finish forming its faces.
That's a cool specimen.
But it's so weird that you this has never been seen.
I've never seen that.
This has never been ever. There's
Never
no other.
looked either.
There's no other examples in the geologic mineralogic world like this. So we're sort of we're here standing and scratching our head. Well, how do you do that? I mean, I think you have to make the faces first before you bump into the walls. That's my guess, but.
And how did it stop right at that moment?
Well, because it had no more room. It ran right into the walls, and so you had no more. You can't bring more fluid in. You can't do anything else. You run out of. Yeah.
Excuse me, what do you think the temperature of that environment is?
I think that the Herkimer diamonds are in the range of 100 to 250 degrees C. At that full range, 100 to 250 degrees C, for making Herkimers. Well, that's another bubble there. Oh, I wanted to point this one out because, see this? This is really flat. And I've always wondered, you find these flat tabular crystals. And I'm thinking, what is this? And you find, some people might have even seen these little flat tabular things inside Herkimers. And it's just, they're weird. And I'm not thinking, well, how do you do that? And one of the ways you can do that is as you start to cool down the hydrocarbon, you form these shrinkage cracks. So you cracks, the hydrocarbon starts to cool, it shrinks, you form these cracks, and the quartz goes right into these cracks. And then it starts to get edges. So you get at the face, this face that's where the sphere is on, this side where the sphere is on, is going up against the hydrocarbon, including having some of it actually go into a bubble. But these edges are in open space in the crack. And so they form crystal faces. And if you were to drop this fragment back down into solution, you could actually find a tabular crystal form inside a pocket. But I was more interested in, let me take you back to something. I have to go way back. There. Look at these. See those? Those are tabular fragments.
I've seen those in crystals.
Yeah. How do you get those?
Magic.
Yeah. Well, I think the explanation I just gave is very plausible. Is that you've got shrinkage cracks in hydrocarbon. You form these little things that fill up those shrinkage cracks, and then some of them fall out and fall back into the solution that's making crystals.
What little I know about quartz crystallization, it builds up around and around, or either right-handed or left-handed. So I'm having a hard time relating that to your explanation for the tabbies then. Because that seems, that doesn't give the helix.
Well, again, talk about that egg that you just saw, right?
That I can understand better than I can
You can't,
the flat.
right? But that is being made. You can see it there. It's being made.
Right.
Right, so how do we make them?
With temperature or?
So I'm saying we have a crack in the hydrocarbon.
But how does that relate to the quartz being
I just don't even know I don't know. I can't answer that.
a helix?
Yeah, I mean, I know that we have right-handed and left-handed quartz. You can have right-handed and left-handed quartz. I know that, particularly with regards to some of the face formation. But I don't know how that relates to a little tabular.
That's a perfectly good answer.
I'm willing to say I don't know because there's a lot of stuff I don't know. So those tabbies are cool anyway. I think tabbies are, I've seen some really cool looking tabbies. Amazing stuff. More spherical, the man with the spherical, talking about spherical features. Here's a quartz crystal that's pressing, giving you this big arch kind of curved surface, pressing right up into the hydrocarbon. Here you end up seeing these spherical features actually on the edge of a crystal. This is a Herkimer edge. And then you can have these domes. They're hard to see, this kind of ugly specimen, but those are round domes. So summing up, hydrocarbons come in a wide variety of forms, suggesting it was mobile, able to coat, able to fill in. How to fix that. There we go, thank you. Hydrocarbon has spherical cavities in it that we showed before, later filled in by quartz and calcite, saying it was viscous, mobile fluid containing bubbles. Round spheres of hydrocarbon, hardened, rigid, or to a rubber-like state, suggest a process similar to making tar balls, like a water washing of the oil by later fluids. And gas deposits in the Finger Lakes district have similar geologic features but no quartz. And there are other carbonate-hosted deposits, oil deposits throughout the world. So here's what we can say. Herkimer diamonds were formed in a cavity-rich rock that contained hydrocarbons, both gas and oil. And it's highly probable that the presence of the hydrocarbons influenced the growth of the Herkimer diamonds in lots of different ways. You know, the bubbles themselves, the fractures, but also the chemistry of the hydrocarbons themselves. And we're going to talk about that. This is the big event right here. After this, we have this baby floater phase. And we think that just there were these tons of, hundreds of thousands of tiny little Herkimer crystals were formed. And this is like, this can fit in the palm of your hand. You know, if you will open up your hand, you could see, imagine all of those just sitting in the palm of your hand. And those crystals that I just showed you, if you start to look at those really close, you'll see little teeny Herkimers included in those crystals. We can find phantom little teeny Herks. This looks like you've got crystal faces here, but this is not. This is full of fluid, and that's a bubble in the fluid. That'll move around all inside here. And this is actually a chunk of salt that crystallized out down in here. Those phantoms are cool. So what if this is a pocket that has Herkimer diamonds in it. They haven't pulled them all out yet. What if we take a sample from the wall of this pocket and we take a sample from the mud down in the bottom of the pocket and we look at those. We look at the mud. This is scale that's over here, and these are rusted sulfide pieces, iron pyrite. But look here. Look across on this mud. Look at all these tiny little Herkimers all over the place in the mud. Now let's look at the wall rock. When we clean off the wall rock, this is a single second phase dolomite, you can see all of the sparkle all across here. And if you look at it a little closer, you can see that they are tiny little Herkimers all over the place. That's what this is, this coating. This is a little denser than the one you just saw, because they are all clumped together here. And you get really close on this, you can see this is not that mountain pyramid druze that we saw before. This is something different. This is a coating of tiny little Herkimers. And often when I find these tiny little Herkimers in contact with wall rock, it is ugly. I mean, this is, again, people throw this is ugly, you know? Nobody wants to take that home. But if I get up close and photograph it, look at this. Look at all these little Herkimers, sort of stacked up on top of each other, and they're all around in here. And to give you a size reference, this is your first druze, that mountain pyramidal druze, and here's the same pyramidal druze with a penny. So you can see how big one of those little mountains are. So you can imagine what size these guys are. And let's just, do these things get smaller? Well, we're going to look at just one pyramid, which is like about that much of a penny. We're just going to look at one pyramid. We're going to look right here in this area, and look here. Look what we have. It's hard to see. You can see a couple of faces. But this is just a stack of really tiny Herkimers. And again, the rock, when you get it, the rock can often be very altered. You'll pick it up, it'll be super light. You'll say, well, how come this is so light? And you'll see the second druze and the baby floater or seed crystal druze. You'll see both of those often when you get this rock that looks like that. And the rock will be just chock full of all these holes, just where it's been leached out. You'll find the silica like throughout the rock. And in the most altered case, it'll have no rock, and all you'll have is just the leftover silica cast, leftover quartz cast. So in terms of the summary of this seed crystal evidence, we find lots of small Herkimers in pockets. And they're just at a great frequency. And some of them we can find as a druze, and with this altered rock. And find phantoms inside larger Herkimers. Also, a baby floater Herkimer was found inside a fluid inclusion, inside a Herkimer diamond, the point where we could pick up the Herkimer diamond and wiggle the little baby Herkimer inside the fluid and have it actually bounce around inside the fluid. And a guy said he was going to send me a picture of that. I'd love it. That's going to be great to have that so that everybody can see. So tiny quartz crystals in the presence of hydrocarbons were part of the process that helped Herkimer diamonds grow. This is rare. We don't see this in very many places, but I think it's an important part of the process of actually getting original clay as part of this introduction of hydrocarbons, seed crystals into the rock. So we can have this. This is not mud. This is very dense, almost hard clay, but it's shiny, has a little bit of a mica kind of sheen to it. It's very soft, but it's dense and compact, not loose like mud. And here it is, you can see it white, all here mixed in with the hydrocarbon. And this is a second phase dolomite right there. Now, Herkimer diamonds. So we're using the same plumbing system that we did for the oil and the seed crystals. And there's me digging. That's the last time this is my farewell dig to, mostly because of health reasons. And when you find pockets really close to the surface, you know, they're got tree roots and lots of dirt.
That's unusual.
Lots of dirt and
That one was up top.
it was up top.
Yeah, it was.
I know, that's why I'm saying,
Yeah.
that's why he's here.
Yeah, I know.
Because it was an up top, it's the only picture that I ever have of anybody submitting an up top. But this is the kind of stuff that people found back in the 50s.
Yeah.
When we were walking around and digging just a little bit in the dirt. These are the kind of pockets that were pulled out a lot in the early history. But that's why I want it here, is because it's great. It's great for an early picture. And sometimes you run into these guys.
They were hibernating.
Some of the mines now, if you've been in some of them, you know that they're not just on the surface anymore. That they're working down to different pocket zones and using equipment and to take off the layers. And you have these areas where you have pockets, you know, next to each other and down at a deeper level. And in the pocket, you'll find the Herkimers laying down. At least this is from the Middleville area. This is the way they'll look, and you'll have a lot of mud and broken debris. And this is back to Fonda area, where the crystals are really packed in there. That's really common. And this is a hydrocarbon pocket, where you'll see lots of this very, very black material in here. That's a little bit of mud in here, but you can see the Herkimer. There's one there, there's one here, there's another one over there, here. And if you clean that out, wash them, you get this.
Wow.
All of those came from that little space. I mean, they are packed. When you get a hydrocarbon pocket that has Herkimers in it, they'll often be really packed in there. And this another pocket from the Fonda area. You can see how jam-packed these guys are in here. If you take them out and reconstruct it, you'll have this sort of three-dimensional thing where they're all grouped together really tightly in a three-dimensional like sculpture. And I think this is evidence of flow that's moving in a vertical direction as well as horizontal direction. So you have a three-dimensional fluid movement to give you a three-dimensional cluster, which is different than Middleville, where you have these linear and planar. So there's a direction this way also, but they're flat. They're linear and they're flat. And the clusters, when they put the clusters back together, they're not like what we just saw. There are these linear arrangements, linear and planar. They can go in that direction, or this one's coming out at us actually. So this is this flow is more horizontal, and you know, it's more moving like in a very flat, planar direction, constricted flow to move in that direction. We get bugs, a bug zone, and a bug zone is often separate from the pocket zone, or it could be near it. But I've seen it in several mines. I've seen it below the pocket zone. I talked to the Middleville miner just yesterday, Friday, and he said he finds them directly around the pocket, below and around. This is some examples of Herkimers inside these bugs, along with hydrocarbon. And Herkimer occurs in just a wide variety of forms. Obviously, the smaller ones are often clear, but you can, if you had 4 or 5 small ones in your hand and looked at them, they'd all be just a little bit different. Faces a little elongated or stretched in one way or another, just slightly different from each other. Getting a really classic form where you've got nice even distribution of faces is tough to get. And to get the classic form with an S face is even harder to get. different shapes. A lot of these just appeared recently. The folks at Paradise Falls tell me that they're finding these hawk noses over there, which I love. Love to hear that. But these Cumberland form. That's from TCR, and I haven't seen those from anywhere else yet. This tabular form, tabs are found everywhere. They're pretty cool. I think this is actually a hawk-nosed tab. But
Why do you like the hawk noses? Why do you like to hear that?
see that?
Yeah.
Weird, isn't it?
Yeah.
Yeah. Yeah. I don't know why. Okay. Don't know. And doubly terminated ones are really. This is the only doubly terminated one I've ever seen at this from one guy's collection. Because I was talking to Joel, and he says that he normally finds them with broken, like the stems broken off down here, just a single term. This is pretty common for Herkimer diamonds too, where you'll have a termination on one end and then the other end it goes in this parallel growth. And they're fun. This is, if you can get one of these in your collection, if you're collecting Herkimers, you should have these. No, you should have one of these and one of those. Getting those, that'd be tough to get those. Colors. The fractured white is pretty common for the larger crystals. This is that champagne color. You may have seen these with these kind of wisps of smoky. You can see can you see the little wispy wisps? And it gives you this really nice kind of champagne look. These are cool. And the guys at Paradise Falls tell me that they're finding these. This bright kind of red color, red orange. This is smoky. It's hard really to find good Herkimers that have this kind of smoky color to them. That's my brother who found that.
That's me.
and black. Black Herkimers are fairly common. You can find Herkimers filled with a hydrocarbon. These guys are really important for understanding what's going on with making Herkimers. These are hopper. These are called skeletal because you'll have this face that comes over the top of this. At the very end, it'll make this nice face, and you can look inside and see these. So it's like you're looking and seeing the skeleton. That's why they call it skeletal. But these guys, this kind of step down steps that are forming. This is formed because the solution is super saturated, which means it has so much silicon oxygen, so much quartz dissolved in the solution that the crystal is fighting for how to grow. The solutions like to grow on an edge first, and so it fights to grow an edge. It calms down a little, and then it starts to grow a face. Then it starts fighting again and grows an edge. And then it grows a face, and then it grows an edge. And it does this fighting back and forth, because the solution is so saturated. And as soon as it starts to crystallize out, it changes the solution. And then it gets rich again, and then it changes. And you get this rapid changes back and forth with this super saturated solution. And so you get this cool step-like pattern in these hopper crystals. And this is important because if this was happening everywhere, we wouldn't get clear crystals. So we need to do something with this supersaturated solution. We need to do something to prevent this kind of thing from happening so that we can make clear crystals. And there's a reason for that. There's a reason for what's going on. And what happens is, in order to prevent this step-like pattern, in order to prevent it, we add in hydrocarbon. So we add hydrocarbon into the solution, and it acts as a speedometer. So instead of going, speed up, slow down, we got a regulator in there now. So let's go at a constant speed, okay? Let's just grow at a nice constant rate, and let's not have all this step-like stuff happen. And we'll grow at a nice constant rate, and we'll make clear crystals. People often ask me, how come we get these fractured crystals when we get big crystals? Like, it's really hard to find big crystals that are clear. I think that mostly has to do with water. There's just a lot of water in the pockets that people are mining, either professionally or personally. And that water freezes in the winter. And that puts a lot of pressure on the crystals, and it presses on the crystals, and it causes this fracturing of the crystals. And there's a relationship between size and amount of fractures. And that's because the larger the crystal, the more surface area you have, and then the more forces applied to the crystal in relationship of the freezing to the size of the crystal. You also find these things, which are cool. You get these fractures, you get these rainbows. Those are fun. After the Herkimers, we have some calcite events. And there are 3 calcite events. There's the very first event where you have these are called nail's head. It's like that's the head of a nail if you were to look this way. And there's often this amber kind of color. And if you find them in a weathered pocket, they can look like this. And after that, there's this white or sometimes amber, sometimes not as crystalline form as this kind of coating of changing the amber to white. And you also can find these tiny little crystals that can be over the top of Herkimer diamonds. And then after that second phase, you'll find this bubbly, not crystalline coating of calcite. I found this over this, and this over this, and not again. And these are things people wouldn't want to take home. This is just, I had to put this in. Just so cool. That's a calcite piece. Okay, this is the pocket that piece came from. And that's the piece right back there. Okay? Laying in the pocket right down back there. And that's the piece. And this is common for this the nail's head calcite. If you can imagine if you to rotate this like that, okay? You can see can you see that little you see that little top right there? That's this. So if you were looking like this, you'd have all these stacked up like that. There's a parallel growth for the calcite.
I didn't want calcite. I wanted crystals.
The last thing, weathering. Now, as a scientist who's trying to figure out what's going on with Herkimer diamond pockets, if this is what I have to see for the surface of the pocket, there's nothing. Just a weathered rock, and these are pocket stones that you pull out of the pocket. They're just all clunky, weathered, nothing. I don't get much information from that. And if you were to have a clean pocket, then remember I pointed out that angular fragment in the other pocket, surrounded by second phase dolomite. So here's a closer look at one. This kind of angular fragment. That's what these are. These are these fragments of rock that had dolomite and had crystals on them, but no longer. They're just totally white, totally weathered. And you can find pockets that have nothing. Just be totally empty. Now, are they empty because of weathering, or are they empty because of some other reason? This is miners ask me about that. What about void pockets? What are they? So in summary, we create a rock with holes in it. And they're, Mother Nature has done some unique geologic things in the little formation to make that rock have lots of holes in it, just ready and willing to accept the fluids. Then we pump the fluids up the fractures, pump them out into the porous layers, the dolomite being first. We then put in the hydrocarbon and the seed crystals, which is probably a pretty corrosive event, doing quite a bit of etching and leaching of the material. And then we enter this very super saturated fluid, high in quartz content, high in salt, and we start to grow the Herkimer diamonds. Why are the mines a little bit different from each other? One reason is because of this sequence. We have this sequence of mineralized episodes, but the sequence is a little bit different in each mine. You almost wouldn't expect this sequence to duplicate exactly in intensity in every mine. You know, some mine would have a little bit more of one fluid episode, another mine would have a little less. And so slight changes and variations in the amount or intensity of each of these episodes at each mine helps to explain some of the differences that we see in the mines across the district. The second reason, and this gets to your question, the second reason that we see differences is that each of these mines is probably located not just horizontally as I have here, but probably vertically, that you may be someplace different in this system. We don't know for sure because there's so many problems with trying to know exactly where you are. It's a great question because I've been pondering on it myself for like 2 or 3 years now.
Some areas will be lifted up.
Yeah. Some areas are going to be lifted up and the erosion, the glacier is going to erode it here, some is going to erode it up here. We don't know, but we don't know because we don't have any clear way of measuring where we are in the system. You know, there's not like marker minerals that say, well, you're now at 100 feet. We don't have any clear marker things that tell us where we are. But it's a great question because I do think the mines are at different points, different places in the system vertically. I also think they're different places horizontally, that the mines are different distances from the main fault. Because if you remember, I pointed out that really unusual druze with all of the sticks, like stacking all on top of each other like that. I think that's indication that we're really close because of the way that's formed. I think we're really close. And other indications where we get that flat druze, and the flat layers, I think we're out further into the flat region. And I think when we get horizontal flow, constricted in a bed and horizontal flow, we'll have these flat features. We'll have the Herkimer diamonds growing in a flat direction. You'll have the druze growing in a flat direction. Versus the vertical flow where you have the druze filling up these nice sort of elongated druze pocket that goes up 5 feet in a zone, and you'll have the quartz crystals growing in these nice clusters. And you know, people have been trying to explain these differences with other theories, and I just, you know, I think it's so much easier just to use this. It's a simple explanation. It's also geologically appropriate in terms of ore deposits, which has, you know, been my training and is trying to understand ore deposits. I think there's some fluid chemistry differences when you go from the hotter, deeper level along this fault to a shallower level, and as well as when you go out this way. But the problem is we're working in a limestone or carbonate environment, and I've worked in like gold deposits in carbonate environments, and zonation or changes, trying to see any kind of marker minerals in carbonate and changes in carbonate environment, very, very difficult. I don't even know if we're going to be able to solve that problem.
You mean predictable?
I just don't think we're going to be able to solve it because the gold deposits that I looked at zoning, I had to do 3,000 feet to see the zoning in gold deposits in carbonate rock. But I don't think we're going to see zonation changes. I think the only way we may be able to do it is look at the actual rock strata and come to a better understanding of the stratigraphy of the Little Falls Formation. Because the bottom is very pebbly, has lots of sand and pebbles on the bottom, and the top is full of lots of holes and collapsed cave and filled in with debris on the top. So we can kind of get an idea where the top and bottom is. Getting to know any more, I don't know. It's going to take a lot of work. It's a great question. I'd love to be able to see if we can have an answer to how we know where we are vertically in the system. So we have lots of questions, and we've just sort of scratched the surface in terms of our research. As I said, this is a big deposit. You know, I think we're talking 1,000 feet, 1,000, 2,000 feet. It's a big plumbing system. Most of the time, we're just like doing this, you know, scratching along the surface, grabbing a few samples. Really hard to see that huge system when this is our sampling procedure. This is an example of what I'm talking about for a vertical system. That's a man. That red box represents the size of the man. Okay? And if you look over here, this is a big pocket. It's more than the height of a man. Can you see this? Can you see this?
Yep.
Those are vertical features going right up and down. Now here's another group of pockets over here. Can you see the vertical feature? Right there, right here. That you only get to see dramatic vertical features influencing the formation of pockets in the district when you can see this much of a wall. And there's only one place right now in the whole district where we can see that much of a wall. And we're not allowed to go in and see it. Okay? It's illegal to go in. I've personally never been here. So
Is that the Hanson mine?
this is HBQ. Yep. Hanson benchmark quarry. And you know, if you can imagine that if let's say you were mining in Middleville, okay? And that this is all you were looking at from about here to there. Okay? And you saw, oh look, these are along this sort of horizon, aren't they? Look at that. The pockets are, so you'd say, well they must be controlled by that horizon, right? And that's, I think vertical structures affecting mineralization are really important for the district. And what I've heard I had a guy tell me at TCR, told me this story. Because at TCR they're mining a layer like this and chasing along the pockets like they do everywhere in Herkimer. They'll find a zone and they'll just strip off the layer and chase it along. So he's chasing along the layer and he says, I hit this pocket full of rust and hydrocarbon and it went down 5 feet. Just boom. The whole bottom of it fell down, and he said he pulled out a dozen lunch bags, quart-sized Ziploc bags, you know, like what they're like that. He filled a dozen full of Herkimers from pulling that out. But trying to explain that drop down, I've heard people at Fonda tell me they've run into some things like that where they'll hit a pocket that just drops down below the layer. You know, that's this influence of these vertical features when you run into that. This is what I want to study. I want to do a lot more work and looking at those things and understanding them. Now this is what I think I'm going to see in some of those vertical features. This is a research project that was done in a quarry that's just a little bit down away from Hanson Benchmark. There's no Herkimers in this quarry, but the guy did research and did chemical analysis and temperature analysis and all that stuff, and found these really cool These are called breccias, which means just angular fragments that are cemented in another material. But again, I've been pointing out this rimming of the fragments by the second dolomite. Again, you can see it here, because that's characteristic of this hydrothermal flow, this hot fluids, these fluids that come up the cracks, go around the broken rock fragments that are in the crack, and it's a different, I mean, it supports this idea of horizontal vertical flow and hydrothermal activity in connection to the origin of the Herkimer diamond deposits. This is cool, right? This is a big vertical pocket. That is 3 feet. I don't have a size on that, but that's 3 feet. And there's these big fragments. You know, to a large degree, you know, this whole thing happened because of people helping me out, sending me photos, sending me samples, agreeing to meet me and give me samples, and you know, I still have lots of questions. I need, as I mentioned, I really need photography of the vertical structures and a lot more detailed analysis. I'm looking for more analysis of black hydrocarbon pockets and samples of the wall, samples of the black stuff, pictures of the pocket as somebody opens them up. So, because the combination of hydrocarbons and quartz is critical to understanding the whole district and what's going on. And the more examples I can have of how those relate, the more information I'll have on understanding what's going on. And here's a list of a few other things. Highly altered rock. I'm always interested in looking at that. Black light photos of oil in the Herkimers. Sulfides with drues, really hard to come by. Those two right next to each other. It's difficult I haven't found very many examples. And any samples of baby floater Herkimers as a drues, that's great, because that again is more evidence of this whole theory and what's happening. Lots of people have contributed to making this happen, and like I said, this is a collaborative project, and I'm so grateful to the help from everybody. Questions?
What's the source of the silica?
If you look at slates, like if you drive along the highway anywhere, and you'll see these little veins of quartz that squeeze, they call them sweat outs. This silica, they call them sweat outs because it comes from squishing or squeezing the rock, and the silica comes right out and comes right up fault systems, and that's how we get it.
Okay.
Because you have so much silica,
Right.
you know.
Like in the Taconic.
Yeah, associated with the Taconic. Absolutely, absolutely. Yep. Yes.
I don't have actual proof for this, but in my opinion, collecting for 40 years, how do the isolated pockets get the fluids and the materials in there to deposit either the dolomite or the Herkimer diamond?
Yeah, I had a picture up there with Herkimers in some, like the bugs, Herkimers in some pockets and not in others.
Right.
It's a great question, because I've been asking myself the same thing.
Okay.
Like, you know, and I think if you think about having the Herkimer, when you have a pocket that has dolomite and oil, the Herkimer has a really hard time finding a place to get going. Okay, so I think you need to have those little seed crystals. And I think what happens is that you're not thinking of don't think of the bug zones as being isolated little pockets, but think of it as a interconnected network of little holes that have fluid that you have access to. And then when you start growing one crystal off of a seed crystal and it starts taking over, it wants to suck in all the available silica it can, so it can grow.
I had a guy in Las Vegas, I guess what he did was, dry washing for gold out there. He knew about rocks a little bit anyway. And I told him about the Herkimers that are don't have a pocket, they're just surrounded by solid rock, it seems like. He says, well, the pocket collapsed.
Collapsed pockets?
Yeah, I don't know where he's heard that before, but.
Well, we have a lot of collapsed pockets. I mean, we do have collapsed pockets. That, you know, I showed you that mud, it had all these tiny little fragments in it. I mean, we do have collapsed pockets, but that's pretty common from the weathering. You know, with all that water that runs through these pockets, and it's pretty common to have nothing stay up on the roof, you know, because it just gets weathered and it can't hold on anymore. It just
Maybe the
falls down.
earthquakes dropped them.
Hmm?
Maybe earthquakes over the years.
Yeah, there's been
dropped
plenty
some.
of shaking, right? Yeah.
Or the mile thick glacier, like
That-
at Fonda, like
Pressure.
where the pockets are closer to the
Right.
top. Maybe the heavy glacier.
Or even the heavy glacier going away and having this rebound. Which,
Yeah.
yeah. Sure. All of this stuff can be part of what affected the deposits. But your question is great, because I have been thinking about that myself, because you know, the theory has to be explained how you do this when you have such a difficult time nucleating a crystal. It doesn't want to do it. You know, it doesn't want to grow on oil, and it doesn't want to grow on dolomite.
Right.
So the only really good way we can do it is by having some little seed, some tiny, we're talking half a millimeter, quarter of a millimeter little seed crystal that starts to grow, and you get once it starts to reach some point, it'll take over.
Okay.
Because the surface area will be so great, so much greater than any of the other little ones, it'll start taking over.
It's the oil the residual oil that helps make them double terminated so they don't attach, or is it
Yeah,
combination
exactly.
oil and
Well, you
hydrogen?
remember, we're carrying along tiny little seed crystals that are doubly terminated, floating in the oil and water.
But the oil probably keeps them from attaching
I
to something?
I think that I've seen crystals right inside hydrocarbon. I think other binders will say that they've seen that one too. Just
In the veins.
right
the,
in the black stuff.
The black veins.
Yeah, right in the black stuff. Yep. Yep. Yeah.
I don't mean to dominate.
No, go ahead.
Well, we love the questions, yeah.
As a paleontologist, I question you calling those structures stromatolites.
Okay.
Because they became extinct pretty much at the beginning of the Cambrian, after so many billions of years of dominance.
Okay.
Aren't they stromatoporoids, which are sponges
Well,
rather than algae?
well, you know, I communicated with a guy named Ruth, who has come up with a new theory about stromatolites, and talks about different changes in the structure of stromatolites based on the type of environment in which, like if it's a salt environment or Sabkagan environment, or a deeper water, fresher water, whatever. And he has different terminologies. So I would agree with you that he has slight different terminologies for, and if we wanted to become strict on it, I would say yes, they're slightly different, and there's different terminologies for them. But I didn't want to go into that kind of detail.
Okay.
Yeah.
Well, I loved reading about stromatolites, and they do have a couple areas in the world still where there's some. And
Right.
They're in hypersaline areas, and Shark Bay, Australia is one, and I think I can't remember the other right now, but Shark Bay is a classic one. And it's hypersaline, just like you said yesterday, that the bubbles, the Herkimer bubbles have
Yes.
more
25%,
saline,
yeah.
which goes along with that.
Yep. Yeah.
And where's Paradise Falls?
Oh.
Somewhere, right?
Middleville.
Mesmore, Middleville?
That's not a public place.
No, private property.
Oh, okay. I'll get out and try.
Well, TCR, I spent like 6 months at TCR, per courtesy of the owner, until he got really upset one day and said, go.
What's
And
TCR?
Turtle Clan Ridge.
Oh,
And
that was
we
my
haven't
fault.
we haven't even seen any material from there. You know, he hasn't even released it to the public.
Are you the
It
younger
was,
brother?
it was my fault.
Huh?
It was my fault.
I'm not blaming you because everybody that knows these guys knows that they're just a little. They have a different perspective on life.
Yeah, but when we pulled out that big
They're
skeletal.
good people. They just have a little different way of looking at things.
We pulled out that big skeletal out of that. He used his dozer, his machine, cleared off the top. I went in there, pulled out a crystal, and then.
But what's nice
Yeah.
is that he has exposed a lot of different areas with a total vertical relief of probably 100 feet, and then a horizontal relief of probably 400 feet. And so he was able to take me around and explain what he's seen and show me different things.
That was
And
fascinating.
so I've had a lot of the photography you probably saw at TCR written next to it. You know, that's why I said in that mine I thought I was right really close to the fault. And that helped me be able, that's why I've come up with this idea that I think when you get really close you start to see some differences, because I saw so many bipyramidal quartz, you know, these little Cumberland quartzes all over and bugs everywhere.
Yeah.
And you don't see that anywhere, nowhere in Herkimer. You don't see these, that doesn't happen. So something's weird, you know? It's a little different there.
That was fun.
Can we send photos to
Yes.
herkimerhistory.com?
Absolutely,
Okay.
absolutely. In fact, if anybody wants a card,
Please.
because I love to have
Great.
contributions.
Great.
And you have a spot for uploading pictures?
Definitely.
You have a spot for uploading pictures?
No, they just send them to me because I have to choose what I
You
want.
just send by email?
Yeah,
Okay.
send them to me by email.
Okay.
Yeah. You just go to find the contact button on this site and just send
So
it.
those little
Thank you.
teeny red things are oil globs, huh?
Yeah.
I wonder what those
If
little
if you find any of those,
you'd like some red things?
yeah, photograph them or photograph them first and then send them to me.
I
And,
thought somebody melted plastic or something.
oh, that's really nice.
Isn't that beautiful?
Oh, I'm in the way.